is functionalized. Sorry. The graphene is also functionalized using Triton X100. In this slide, you can see the you can see the functionalization of the graphene. Basically, I will not go through it, but at the end we get the functionalized graphene. Then here you can see in this slide the manufacturing process. As you can see, we start with functionalized graphene. We add epoxy resin, and in the magnetic stirrer, it is stirred 15 minutes. Then using the 3-roll milling, we mix it, and then hardener is added. Again, magnetic stirrer is used. It is molded and cured at 80 centigrade degrees for 1 hour, and then 160 degrees for 4 hours, and we get the specimen. And this is the procedure that we follow in the manufacturing of nanocomposite specimen.
Hello, doctor. Sorry to interrupt. Your slides are not moving.
It is not moving? Oh, sorry.
Yes. Could you make a next slide?
Let me stop and share again.
Yes, ma'am.
Okay.
Sometimes you have to do it manually, so need to do next.
How is that now?
Yeah, it's fine. It's a material and methods, right? Yeah.
Okay. Yeah, this was the functionalization procedure, and this was the manufacturing of nanocomposite specimen. As I mentioned, this is the procedure that we followed. Now, is it? Can you see the next slide about the compression test?
It's a specimen production.
Okay, now. Now, in my case, there is a compression test, CRIP, and DMA. Can you see it?
No, ma'am.
No? What happened? Let me without. Maybe I should go this way.
Yes, sometimes your internet is okay.
How about this way? Can you see?
Yeah, mechanical. Yeah, okay. Correct.
Maybe I should go this way. So following the manufacturing process, we have done mechanical characterization, and we start with the DMA, dynamic mechanical analysis, quasi-static compression test, and CRIP tests are performed. In the quasi-static compression test, we perform the experiments at different strain rates because graphene-epoxy or polymer matrix composites are rate dependent. So we wanted to investigate the rate dependency. And CRIP experiments are quite important. So that's why we performed some CRIP experiment at different stress levels, and the DMA also another test that we have performed. The work consists of manufacturing, mechanical characterization, and modeling. And the model that I work on is called viscoplasticity theory based on overstress, which is initially developed by Professor Erhard Krempel. So I just wanted to acknowledge him. I would like to give a little bit information on the model. I will not go in details. Basically, the final form of the VBO model is called cooperative VBO for polymer graphene nanocomposites. And on the left side, you see the deformation, rate of deformation tensors. It is additive of elastic and viscoelastic part. Cooperative VBO consists of 3 state variables. One of them is equilibrium stress. The second one is, I cannot, let me, sorry about that. Anyway, Equilibrium stress is another state variable. Kinematic stress and isotropic stress are the other two variables which are present in the model. Okay. Sorry. Okay. So viscoplastic strain rate is defined, internal stress. As I said, I will not go in details of them. I would like to mention about the elasticity modulus, which is temperature and strain rate dependent. The material parameters in this elasticity modulus is determined from DMA and some more formulations about these transition temperatures that we obtain from DMA and some more. Basically, a VBO model has been developed for polymeric materials, but later on with some modifications, we are now able to model the nanocomposites as well. And for that concept, we use the Mori-Tanaka micromechanical model to be able to include the effect of reinforcement. These are some bulk and shear modulus for the matrix and some other parameters related to heel parameters, etc. And basically, if I remind you, this was the elasticity modulus, which was valid for polymeric materials. After using Mori-Tanaka scheme, basically elasticity modulus, effective elasticity modulus is defined considering the formulation that is given before. And these are some more formulations. And again, for the viscoplastic part, Takayanagi averaging scheme has been used. In this case, the effective activation energy and effective activation volumes are presented, and they are written in terms of reinforcement and matrix materials. If we look at some of the simulation results, this is a storage modulus versus temperature curve. This is basically a result of the DMA, dynamic mechanical analysis. And as you have seen, this dotted line is experiment and the solid line represent the model. Graphene is in the amount of 0.5% as a weight fraction. And as you have seen, the storage modulus, change of storage modulus with deformation has been simulated quite well using some of the parameters that we obtain from DMA. We simulate the next behaviors. In this slide, you can see the true stress versus true strain curves for two different strain rates. One is 10 to the minus 1, the other one is 10 to the minus 3. You can see the very good match with experiments and the model. In fact, this behavior is not an easy behavior to model because initially we have a linear behavior, there is yielding, some softening, and then hardening behavior is observed in the materials. So with this cooperative VBO model, we are able to simulate all these behaviors quite well, even though there is some discrepancy here. In general trend is quite well simulated. And creep experiments in this slide, you can see the creep experiments. As known, creep behavior depends on stress level. So that's why we perform the creep experiments at 50 megapascal and 100 megapascal. If we look at where is the 50 is in the elastic region and 100 is close to yield point. So basically in the even though we are in the elastic region, we can see the effect of the stress on the creep behavior. And the creep time for these experiments is 2 hours. And of course, as known, when you keep the stress constant in the creep, strain is increasing, and this change in the strain with time is observed, as you can see here. For the 50 megapascal case, there is some discrepancy. However, when we look at the 100 megapascal, this behavior fairly a good match is obtained in the change of strain with time. So these are the creep results. If we conclude, optimum enhancement in the mechanical properties are achieved when the filler material is uniformly dispersed in the matrix material. As I mentioned, important thing in the nanocomposite manufacturing is uniform dispersion of the nanofiller. So when a 3-roll mill is used, good dispersion is obtained. Even though I haven't presented here, we had some SEM images which shows that the distribution of the graphene is quite well. And another important thing that you have to do in the manufacturing of the composites, nanocomposites, is you have to improve the bonding between the graphene nanoflakes and the epoxy matrix. So for that purpose, graphene is functionalized using the Triton X100 as a surfactant. And then viscoelastic and viscoplastic behaviors are modeled using the cooperative VBO model for nanocomposites, and storage modulus versus time, stress strain behavior under compression test, and creep behaviors have been simulated, and they are compared with the experimental data, and quite a good match with experiment are obtained. And this work has been supported by TÜBİTAK. The project number is seen here. So I would like to thank you, everybody, for listening. So if you have any question.
Thank you very much, Doctor, for your presentation. It's interesting what you have done. I'm going to ask the audience if they have any question for this presentation. Thank you, Doctor. I assume we don't have any question for you.
Okay, thank you very much.